Hey everybody, and welcome to C.R.E.A.T.E seminar. This talk we will focus on automated assessment of transportation infrastructure, mainly focused on the surface transportation and some of the offshore structure inspection. First, let's outline the content of this presentation. We will give some of the brief introduction of the multimodal asset survey, then spend some time on the pavement condition data, include the traditional practice for survey and automated survey technology and equipment. Then give a brief introduction of the future trend. Then I will leave about 15 minutes for the question and answer section. The multimodal asset data collection, when we talk in the multimodal, we really include the air system and surface system and maritime systems. In this presentation, we are focused mainly on the surface system, include the road, a bridge, a tunnel, right-of-way inventory, and other service. Then we will leave a few minutes talking about the maritime systems, include what the technology we used for the offshore structure inspection, and we will play a few video to show the application of the inspection technology. So the first, pavement condition data. This is mainly we're talking about the surface asset survey. The first one, is the surface distress. It's the most content on the surface distress, and is what you can see on the road. And the second, we're talking about the profile and smoothness. It's mainly for the international red quality data inspection. Then few slides for the routing, then texture, deflection, skater resistance, and spotting data collection. Traditional practice, you can see the middle of this picture. This is the kind of the project level of the surface distress survey. Is rarely used, only for some of the research. For this, the right side picture, this is a very typical, they call it the visual survey practice. It's a one driver and plus the one reader. The one reader holds some of the instrument to count what they see on the road. The requirement is you drive the vehicle with below the 15 miles per hour speed, because some of the surface distress, like the cracking, if you drive fast, you can't see it. Your eye delays can average the crack out. So it's required you driving 15 miles or below. Another massive data collection for the surface distress use the manual method is the routing. Routing is the longitudinal depression of the road surface, as shown here at each wheel path. The manual inspection typically use a 6-foot straight edge, and also sometimes they use the step gauge to, if you insert this step gauge and the straight bar, it indicates what the level of your routing is. traditional practice for the roughness. There is no fast way you can use to do the network level, but this for the project level, you can use the rod and the level survey, uh, and also the rod level survey, and also you can use the profile graph like this one, and also you can use the deep state to do a longitudinal profile. Just go along the road to see the up and down. Then the texture. The texture, there's a few standard and governing this practice. One is the old traditional method called the sand patch. And basically you use some of the standard sand, you spread the sand and spread them on the surface to a circle. Then you measure the size of the circle. Then there is a formula you can use to calculate the value of the MPD or MTD for the surface texture. In the middle for this one is called the circular track meter, the CTM. This is a standard instrument. There is a circular laser sensor inside of this sensor. It measures the circle and give the similar value of the texture data. Automatic survey from the roughly from the end of the last century, you start to see some of the instruments mounted on the vehicle, driving at high speed to do the surface condition, road condition data collection. We will introduce this technology one by one in the following sections. First, surface distress is mainly we see is a crack. After the 1990 or the early 2000, the people started using the special camera they call the line scan camera here to do the web scanning. The principle of the line scan camera is the camera is only have the one line of sensor. Then you point this camera to a target. You move the camera, either move the camera or move the target. Then the line will collect the image one by one line by one line. This technology enable people doing the unlimited distance scan of the surface condition, surface image. Then you collect the image, you do some of the image processing. Like here is bottom gave the two example of the line scan camera image on the pavement. This is the 2K image. It's transversed in the one line. You have 2,000 pixels. From today's point of view, this is considered the lower or the middle resolution systems. Here is gave two examples. One is a very famous Enron vehicle. It's developed by the Canadian company called the Roadware. Another one, this is the vehicle system developed by the UT Austin. They use the Dallas City. Here is some example. In 2004-2006, UT Austin and TechStart jointly developed the world first massive developed real-time cracking detection system, use the line scan technology. This system can scan the road at 70 miles an hour. give the real-time processing of the cracking. At 2007, Textile built the 12 of the systems doing the entire state data collection for every year. At the bottom, there is a two processing, the processed result. You can compare the raw image and the processed result. At the network level, at that time, this considered a pretty good result and gave it a pretty good accuracy. So the line scan cameras only gave a surface picture. There was no structure information. There's no 3D data. Then from the 2009, the Textile developed its own 3D systems to do the RAT and surface distraction inspection. That one is also considered the world first 3D image-based pavement surface distraction survey system. The basic technology here is you see this is the laser line, the line projected to the ground, and the camera see from an angle. In the image here, you see the square. The laser image will change the shape in the camera image. The shape size is roughly related to the object height. Based on this technology, it's very popular in the transportation inspection. The people use this technology with a laser camera to grab the 3D picture from the surface. This technology is called the laser triangulation. This system is a very famous parametric system. It's the world #1 sold system in the market. This one is the Textile vehicle. It's built by Textile in-house project and used for the rotting and cracking detection. Here is the bottom. Here is a few images. A 3D rolled 3D sensor system can produce two kind of data. One is a picture like. It's like you take the camera, take the picture. We call this intensity images. Another one is called the range data. Range data here you see is the dark side means the lower on the surface. The bright side means the higher in the surface. So you can see clearly the cracking on the surface. And also this is a rainbow 3D display just for the visual purpose. So some example you can see from the beginning of the 2009 Textile system have the 1.5K resolution. This means over the whole line width, there is a 1,560 pixels. So each pixel is roughly about 3 millimeter. Then it's gradually improved to the 4K system. So that each pixel have a 1 millimeter space resolution on the road. It's considered this very high resolution. Here is the two example of the pictures from this 4K system. This is the intensity. The left is the intensity image, and the right is the range images. And you can clearly see the letter of the manhole cover. And here you see the crack. You see the crack on the surface. And also with the 3D system, you can also do the routing. This is a result of the routing processing. It's a long way. So each dot here is a 40 feet. This is a pretty long road. The two colored lines showing the measure the routing depth, the route depth with a different color. So the red one means the severe route is the deep, and the green and the yellow means the shallow route. We will talk the route especially on the next pages. So the other distress is the 3D systems also can do. Like here is the sealed crack. We can process the sealed crack from the intensity image, and also the pothole. The pothole is a very severe problem on the road condition. So the the system can use the range data, the 3D range data to do the pothole. This is a patch, and the patch is also considered a data needed to be collected, but the patch have some of the unique features. Some patch is really, really big. It could be a 100 feet long, and also if a well repaired patch maybe have no elevation difference to the surrounding area. So the reliable detection is mainly from the intensity. Uh, Here, if they use the same color material, then there will be a big challenge for the auto processing. Irreveling. Irreveling means the lost aggregate on the surface, especially on the chip seal or seal coat in Texas. We give the name of the chip seal seal coat in Texas. This one is flashing. Flashing means the when you do some of the pavement, you overuse some of the bending material like asphalt. So the asphalt is popped up due to the traffic and also due to the heat popped to the surface and make the surface is kind of a tar-like. When it's a rain, this one could be a very dangerous with a very low skid resistance. The smoothness. The smoothness, the IRI means the International Ride Quality Index. The IRI is calculated from the longitudinal profile. The standard way to do the longitudinal profile at these days, we use the inertial profile, like here in the front bumper, mounted on the vehicle, driving the vehicle on the surface to collect each wheel path profile, because the vehicle will follow the contour on the road. This means the vehicle will bouncing up and down. So we need some of the reference to remove the vehicle vertical motion. Then we use the accelerometer to get the acceleration. Then we calculate the movement of the vehicle to remove the vehicle bouncing. The problem is the accelerometer have the feature when it's traveling at a low speed, like below the 15 miles an hour, the accelerometer encountered a problem with the low speed of vibration. So this the network level data collection still have a challenge for the low speed. So we also call this the stop and go traffic condition, especially in city environments. You often stop in the traffic. You also stop in traffic light. Then make your data unusable. So it is still a challenge now. So the routing used the 3D. You see that in the old days there is a point-based route bar like this. The picture shows. Each route bar contains 5, 7, 16 sensors and give you roughly give you a profile, transfer the profile. Then you do some of the calculation for the route. Now the people use the 3D. 3D give you the transfer the profile. Then we developed some digital algorithm to attempt to do the same thing like the straight edge. Then you find the deepest point. You give a string here, digital string here. Then you measure the depth of the route. This is the textile route vehicle, 3D route vehicle, and developed on the 2009. The macron texture. The texture is used to estimate how rough of the surface the people can consider if there is enough roughness, enough texture to provide good skate resistance to prevent the skate, especially in the wet weather condition. Nowadays, there are two ways use the instrument to do the texture. One is use the stationary laser scanner to scan the 3D surface. Then you can do the texture MPD or MPD. This instrument is the laser scanner and developed by the Huang to do the texture. This is the textile laser sensor to do the high speed texture measurement. The critical condition use the laser sensor to do the high speed texture measurement is your explode time must be very, very small. Otherwise, if you open the laser for a long time exposure while you drive at high speed, you basically you average a section of the road for the texture. Then you lost the details, lost the high frequency components. The skid resistance. Skid resistance now is used for a project level mainly because the standard equipment is still something called the lock wheel. Lock wheel you see here is the trailer, skid trailer. This wheel, when doing the measurement, this wheel will be locked, and you drag the trailer on the road. The wheel have some of the skid with the road surface. Then you measure the dragging force from the truck to the trailer. Then you can calculate what is the skid resistance level on this road. To protect the tire, it requires you spread some of the water. Here, like here, this is the water nozzle. When you do the measurement, you spread. See here, you can see for the yellow vehicle here, at the end is spread some of the water in front of the measurement wheel to protect the wheel for the wear and tear. Then there's a joint concrete faulting. This data is indicate to the concrete surface there's a elevation change between the two slabs, like the picture shows here. Now the federal government required the states to do the data collection, include the faulting. So now in this few years, the people start to develop different faulting measurement instrument to do the things. The high speed faulting measurement sensor is from the TechStart. We used for is a line sensor, measure the profile like this one. If you do cross a joint, concrete joint, you have the profile. You see, if you do the data processing, this is the one slab, this is another slab. Then you can have the difference of between the two slabs. Then this is defined as a faulting. After the surface distress, you can see from the road surface. Then there is some measurement also today is conducted. Is the end surface, mainly due to the pavement structure. This means that there is a structure problem. And layer, there is something happened and layer. So there is a group of the pavement structure condition measurement, mainly use the FWD, is the falling weight deflectometer. We will see some of the detail on the next slide. And also the improved FWD is doing something a little faster. Then the ground penetration radar. There is the antenna is kind of the radiator EM pulse to the ground. Then you measure the reflect wave. Then you can build the underground layers of the surface. Nowadays, the developer also give you some they call it the 3D GPR. Then the last three is a continuous. It's a continuous means you can drive the vehicle on the road doing the network level of the deflection measurement. Falling weight. Falling weight deflectometer is a very popular for every DOT. It's basically a drop of weight. It's a drop of weight. Use a line of the sensor to pick up the vibration. Then from the vibration, they build the reflecting time and the magnitude. Then we can calculate index for the falling weight measurement. This is the sensor used for the FWD. The fast FWD is the old traditional FWD used the hydraulic mechanism to lift the weight. The fast one used the motor, some kind of the linear motor to lift the weight and drop to the ground. This is about 3 times faster than the traditional FWD. GPR, there's antenna and the receiver. The antenna radiate the pulse to the ground, and the receiver pick up the reflectivity. Here is a picture of the data from the GPR. You can see the different color represent each layer and underground. It gives you a sense how thick of each layer and if there is anything special underneath. There is a vehicle mount called the air coupled. There is a distance between these things with the road surface. You can drive at highway speed. And also the ground coupled means you dragging these things on the surface. You get some of the better resolution, but you cannot drag them very fast. The 3D GPR means that they put some multiple sensors. The 32 sensor covered 8 feet, give you the something picture-like the result. This use the same principle but it looks like a picture. Give you the detail of the full lane width and the ground structure. This is a new technology called the WaveSense. It's developed by the MIT Lincoln Laboratory. Then there's this is built with some of the sensor can detect underground layers, but the resolution is higher than the GPR. Now there's a company called the GSSI. They bought this WaveSense technology. They developed their own equipment called the LGPR. It is still under the test section. Hope these things will soon. We can see this from on the road. There is a link here, and you can check the detailed. And basically for this example, they use the 12 antenna, give it a 2 and 3 meter depth. It is supposed to be a low cost than the traditional GPR. Pavement structure. Structure means on the surface something changed because they cannot. Some of them can be collected at the same time with the other distress. Some of them need some special equipment to do it. Because the time issue, I will skip some of them of this to do to finish the presentation. The transverse profile is also related to the routing measurement, and also there's show here is the manual method is the beam, and they move a laser sensor along the beam across the line and collect the transverse profile. This is the kind of a rod bar they use the multiple sensor across the line. This also a 3D system to collect the transverse profile. The transverse profile so far, I see, the purpose is mainly for the routing. And also the cross slope. Cross slope means some of the road built with a tilt, like if you have the big turn, the curve on the bridge or on the road to balance the centrifugal force. You need the vehicle have some of the tilt. We call this cross slope. Cross slope measurement now. You can use the manual method. You use the level sensor, and also use the 3D system to get the profile, and also through some of the reference, the horizontal reference. Then you can do the calculation of the cross slope on the road. Marking inspection. So the marking, the landmark, you can see there is some equipment used for this inspection. Marking reflectivity is also used some of the optical sensor to see how good of the reflection from the marking. Guardrail. Guardrail is also some department want to see the guardrail. They use the LiDAR. I bet you already heard a lot of times for the LiDAR. The LiDAR have the different level of professionalism. Some LiDAR can give you the really detailed 3D structure on your road. Then you got to process this data. So how good of the guardrail and other structures along the road. Sign inventory is also interesting topic. for the DOT. Mainly they use some of the camera uh, and also the sensor to detect the sun and see how bright all those suns. Some company use the 3D sensor to find the sun, then do some of the sun reflecting, doing the sun type. I'm thinking now that a lot of the companies start using the AI to to classify, to identify the type of the sun. Sun reflectivity, the same thing like the sun inventory. Tunnel inspection is interested in a lot of countries, like in the Asia, like in the Europe, especially in China, Japan. There is a lot of the tunnel, the highway tunnel. The U.S. the tunnel number is relatively kind of small. This is a typical systems to do the tunnel uh, inspection. Basically, they use some of the image system, line scan image system, to scan the tunnel internal surface to check the cracking and also the structure. Uh, this is the sensor built by our Hamid, used for line scan camera to scan the entire tunnel to get the high resolution image for the cracking process. You can see here is the example is for the subway tunnel. They use some of the multiple sensor and moving cars to do the subway inspection. 3D 3D tunnel inspection is now still under the development. This example is a Pavmetric and a company from Spain. They use the six. They use the multiple 3D sensor. They do the internal internal inspection. This I'm consider this is a very expensive equipment because when this sensor used in road surface, uh, they kind of the 200,000 for a pair. So you can see how expensive this equipment is. Also the LiDAR, the high resolution LiDAR can give the structure of the tunnel, but because the nature of the LiDAR, uh, this is still not good enough for the cracking and some of the detailed information. Uh, Here is the video for the underwater images. I'm going to drag into the 20 second. Okay, this is the manual inspection, and also we see to use the robot to do the photo inspection here. Okay, I'm going to cut this off because we are running out of time. So doing the underwater inspection, I'm seeing there's three technologies you can see on this page. The first is the image technology. You use a camera for or use the 3D camera. For example, this one is uh, uh, this stereo vision. Use the two cameras to take the picture underneath and build some of the 3D model of the underwater structure. This one you have to say you need some clear water. If the water is muddy, this one won't work. And also this second one is the sonar. There is a sonar sensor to go under the water and you can scan the structure of the water with some of the distance. Either you submerge the sonar sensor underwater or from the air. You use some of the drone from the air. And remember this the sonar sensor, the resolution is kind of low. You can't expect this one doing some of the cracking, doing some of the detailed things. But it's good. It can scan the largest structure underwater. So there is another topic is developing the new days. They call the multispectral and hyperspectral images. It's basically it's one from a special camera. So the one shot is give you 1,000 of the pictures here. You can see from the right here. Each picture is under the different lighting condition. So the light is give you the different wavelength. For example, the first one maybe from 100 nano is going all the way to some of the 1400 or the something. There is a nature of the material. They have the different reflectivity and the different wavelengths of the light. These things can detect very special object is sensitive to some of the special wavelengths. Yeah, for example, if you do the agriculture or like the offshore wetland, you take the picture by the different wavelengths. You can do analysis of the vegetation, what type, and the water content, and also if the image is health or have some disease. You can from the air use the drone, take the big pictures. And also if you take the picture of the waterway, you do the analysis from the different picture and the different wavelengths. You can analysis the mineral content of the water and also the banks and also the water quality. There is some special material in the water or some special grass or also some of the special species and the growing on the wetland. The bottom here is application is used under the water. Under water is you see from the different picture, you see the different content. If you know what type of the light is sensitive to what kind of the wavelength, then you can learn what is the animal, what is the grass vegetation in this piece of the ocean bottom. Again, there's still a technology and the development. You can buy the camera, you can buy the light, but you need to develop your own interest or reason to extract information from this pile of the images, thousand of them. The multi-spectrum and the hyperspectrum is the difference. Is the multi-spectrum have a nice pictures with a one shot, but the hyperspectral is considered continuous. It can take up to 4,000 or more pictures at the one shot. So this will be interesting for the offshore land management in the future. Future trend improve the data quality, use the AI, like I said, the IR measurement for speed range, and also some better things with the DOT need. Okay, this is the end of my presentation. So any questions?